Hello everyone! Today I'd like to share with you how I ported code on a physics simulation from Godot to Unreal Engine. DreamJump game dev, who uploaded an amazing tutorial on how to make your game feel more alive using Spring Physics simulations, which, by the way, he is going to use in his commercial game that's gonna come out hopefully soon, Tyto, a game about an owl, in which it just looks really amazing, and I recommend all of you guys to follow him and check out his game. Back to our subject, I watched his tutorial on how he implements physics-based springs in Godot, but I ported it to C++, specifically to Unreal Engine's user widget system. In this tutorial, I'm going to talk about the project that is linked in the description with the GitHub repository, in which I implemented a physics-based simulation on a user widget in Unreal Engine. We're going to talk about everything from creating a C++ class that inherits user widget. We're going to talk about binding widget objects to C++ and manipulating them from C++. I will touch on some key concepts of general C++ development, and everything is going to be split into timelines, so you guys can choose which parts of the video you want to watch, especially if you plan on downloading the project from the repository and there are some parts that maybe you don't understand. Feel free to ask questions, and of course watch this video in which I'm going to explain exactly every piece of code that I wrote for this project. I hope you guys are going to enjoy watching this video and also find it insightful. If there's anything that I say that is wrong, please point it out in the comments, and enjoy. Alright guys, so let's talk about what a widget with Spring Physics exactly is. As you guys can see, the Unreal Engine logo is here, and I can change its properties. I can adjust its shear value or skew value, however you want to call it, just by positioning my mouse to the right of the widget or to the left of the widget. When I click my mouse, I'm going to adjust the value of the shear, and when I release my mouse, we're going to start a physics simulation on the shear values. Now, if I set the checkbox for SpringScale, I'm going to be able to adjust the widget's scale the same way. Whenever I hold my mouse to one of the sides of the widget, the scale changes accordingly. And when I release it, the widget bounces back, springs back to its original state. Same position, I can hold my mouse, move the widget around. When I release it, it's going to spring back to its original position. So let's talk just a little bit about the math behind the physics simulation. We're using Hooke's law together with friction to implement this behavior. The spring constant is the constant usually used as k in Hooke's law, and when we set a really low value for it, we're barely going to get any spring behavior. As you guys can see, the movement is getting dampened, and the spring we don't even get spring behavior. If we don't put any dampening, we're still going to get spring behavior, but since I'm not dampening it, it's going to continue to infinity to keep springing in a very low power. The more I raise the power, it's going to spring more and more. And I've got an event set so that the change of values instantly changes also the values in the widget. Right, and the value of 204.5 are just the values that I played around with, and I found them to be to get the desired behavior that I like for the spring. And I want to talk about the mouse effect, which is just an arbitrary value that I made up to change the amount that when I move my mouse, how much is it going to affect the widget. So let's put it to 0.2. And we see that the amount that I move it starts changing the widget much more. If I put it even higher, it's gonna really change the size of the widget. So I'm gonna go back to 0.1. And by the way, since we're using the SpringScale, we've got an interesting technique that DreamJump game dev talked in his tutorial. And it's that the The Y scale is exactly the opposite of the X scale. So the more we make the width of the widget bigger, we're actually gonna scale the height to be smaller. So the more the width gets bigger, the height gets smaller, and vice versa. The more the height gets bigger, the width gets smaller. This actually results in this kind of behavior that if we start putting big enough values, the scale is actually going to get reversed, and we're going to take care of this in the code part. I want to talk real quick about what we've got in the editor here, so better to understand while we're going through the code what we're seeing. We've got a canvas panel here with a image inside. The important parts are that the canvas panel is called canvas panel root, and the logo, the image is called logo, because we're going to actually bind the canvas panel and the logo onto the C++, onto the code. Then we've got a wrap box containing texts and editable text and checkboxes, which will also affect the booleans of the code. And lastly, I want to mention the canvas panel slot here, which is also a variable that I'm gonna get from the logo variable in C++. We'll get to it real quick. I just want to mention that it is shown here in the editor. We can see it. It's the property that connects the logo, the image, to the canvas panel, and this canvas panel slot actually holds the information on the position and on the size of the widget. Alright guys, it's finally time to get into the code, into the meat, but we've got to do one little thing that I want to make sure that you guys are aware of. Is we go to the project.build.cs file, as you guys can see here in the content browser, and we've got to do this little thing and add the UMG to our dependency module names. We just go to this line in every project.build.cs, you're going to see it, and you just write like so, UMG, and we're going to be able to use the contents of the UMG library. So let's go dive into the H file first and talk about the declarations and what we're going to use. The most important part that I want to mention, in my opinion, is the ability to bind the editor's widgets to the code in C++. So as you guys can see here, we've got the canvas panel root and the logo, and these are the objects that I mentioned before that the names must be the same, that I want to bind to the editor. Again, instead of using a tsub class of or something like that to specify the class to load, here we're actually binding the widget object to our reference here in the editor. So I'm creating a tObject_ptr, which is a smart pointer. You should always use those when you're declaring pointers in as class members. And it's going to be a pointer of type uCanvasPanel with the name canvasPanel root. And then in the uProperty specifier, I'm going to write meta equals bind widget. And that's the punchline. This meta makes this variable be bound to the object, to the widget object in the editor. We could also use another uProperty called bind widget optional. And the difference between bind widget and bind widget optional is that bind widget will force the editor and it will throw an error and it will not let the blueprint compile. Contrary to that, bind widget optional is, instead of throwing an error, it's gonna show a warning. So this bind widget optional cannot guarantee that this variable is gonna be set, but when I use bind widget, I'm guaranteed that if the code runs and the blueprint compiles, this variable is existing and I can use it. Let's take a look at an example of how this bind widget meta works. And I'm going to break the widget binding right now in the designer, in the blueprint, I'm going to take the canvas panel root here, and I'm just going to rename it to canvas panel amazing. Okay. Now the amazing canvas panel for some reason does not compile. Here we get the error, a required widget binding, canvas panel root of type canvas panel was not found. And this error here is created because of the uMeta property here, bind widget. That's the reason that this error is being thrown. And when I go back to the editor and I just name my canvas panel the way I named it in the C++ file, we're going to get rid of this error and everything works. Then we've got the logo slot, which is, I'm not binding it, but I'm going to get it from the logo and store it. Again, this is the object connecting the logo image to the canvas panel, and it holds the position and size information. And since we're going to be manipulating the widget, its position and stuff like that, I want to use the logo slot. Next, I'd like to discuss the functions that I overwrite from the parent class, UWidget. A very important one is native OnInititalized, because this function, it has some resemblance, I guess, to the begin play or on construct of the actor classes, where we're promised that this method is going to be called only once, compared to the construct event in widgets, which is going to be called each time the widget is added to the slate draw, or some internal widget management thing that I'm honestly not that clear about in Unreal. But here, let's read the official documentation. This method is called only once at game time on non-template instances, while construct deconstruct pertain to the underlying slate. This is called only once for the UWidget, okay? So if you have one-time things to do up front, like binding callbacks and events on bind widget properties, do so here. So this event is basically, this function is for us to set up things for our widget that we want to set up only once when the widget is, well, when it's constructed, but not exactly, when the object is created. Let's put it this way, because the construct function actually runs after the initialized function. Perfect. Now the whole program is going to run on tick. Then we've got OnMouseButtonDown and OnMouseButtonUp, which are again functions that are that I override from the UWidget parent class. Let's check them out real quick and understand what they do. So once the mouse button is down, on the mouse button down event, I set my boolean b mouse button pressed to true. And I also reset the logo. What does resetting the logo mean? It means that I'm going to remove any velocity from the Spring simulation, and I'm going to set all the values to their default values, the shear, the render scale, and the position. Meaning whenever I press my mouse, I want everything to be reset. I don't want the previous, like if there's a running physics simulation, to continue when I'm pressing the mouse, because when I press it, I want the widget to start following the mouse and not run the physics simulation. So all the words I just said, it's equivalent, I guess, to saying that I actually stop the physics simulation. On mouse button up, all I'm going to do, the boolean mouse pressed to false. Notice an important part that the native on mouse button down event returns an freply. And what I did is I just used the freply that the super method of the parent class returns, and then I return it just the same way. I'm not exactly sure what this is, I'm being honest with you, and then I just return it the same way the parent class does. And talk about what we initialize. So first thing first, we've got the variables for the Spring calculations, the Spring constant, damping coefficient, and mouse effect. These are the variables that we've seen in the widget, where we can change them dynamically. This is why I wrote here set up editor variables, and they can be overwritten in the editor. What exactly does this mean? As you guys can see, the variables set here are 01, 5, and 200. But when I'm going to the editor and I'm going to open up the blueprint here, the values I set here in the blueprint are actually gonna overwrite the values from the C++ file. So let's put, for example, let's put here 10, for example. Now, when I start up the game, I'm gonna have 10. Okay, and also, as we can see, the spring force is really lowered compared to 200. And also the damping coefficient I changed to 4.5 compared to the original value here in the C++, which is 5. And when I play, I get the last value that I set in the editor here in the blueprint. All right, so these are the variables that we can edit from the blueprint. Then we've got the internal variables, spring threshold, which is the threshold that I'm going to use to stop the spring behavior, meaning that I want the tick function to stop calculating the physics simulations once the change of the spring is not visible. So for example, if we set the shear value to go like all this way and we start the spring simulation and it goes like this, at some point the spring is gonna get very, very little changes, very small changes, and practically at this point when the widget is the changes are not visible, I want the simulation to stop, right? I don't want the simulation to keep going when the widget is already at its rest position. So practically this is the threshold that I choose, and when this threshold of displacement from the original place is reached, alongside the fact that there's no velocity, we will stop the physics simulation. The spring velocity is 0, is the start value of the velocity each time we start a simulation. It's going to be reset to 0, and we've got a spring velocity vector, which is just a vectorized version of the float value here, which we're going to use for the position calculation. Next, I want to talk about getting the mouse position. There's a small caveat that we must discuss. Let's show how I get the mouse position first. So I create a vector, I call it mouse position screen. And I'm using this naming convention because this I want to mean that the actual scale that I get is the screen scale, the whole screen scale, not just the viewport, not the position that the widget is being calculated at, the whole screen pixels scale. So I do this by accessing the player controller, which can be accessed from any user widget in Unreal Engine. So this function is going to store the screen position X and screen position Y into the vector mouse screen position. Then to actually convert this screen position into the viewport scale or widget scale, I'm going to refer to it from now on as widget scale because this is the actual position of the widget. We take the mouse position on the screen, and we divide it by the viewport scale. And the way I get the viewport scale is I create an fin32 vector 2D. I plug in the X and Y values into getOwningPlayer get viewport size, which then stores those values into viewport size. And then I pass this variable onto get viewport scale based on size, which is a function that I wrote just to shorten the function that Jonathan A. Daly uses. This function, get default user interface settings set a class, get DPI scale based on size. And this function gets a f endpoint as a parameter, and what I do is I convert my viewport size to an f endpoint here, and I pass it on. Then the value this function returns, I return it as the viewport scale here. The important thing to know is that we need to include this h file here, runtime engine, classes engine, user interface settings.h. Of course, by the way, all of the source files are going to be found in the GitHub repository I'm going to share here in the description. Okay, next, the logo slot. We get it using logo getting the slot from it, and we cast it to a UCanvas panel slot. This is not the safest thing to do, but since I know that my logo is under a canvas panel, I know that its slot is a canvas panel slot, and I'm gonna also show it real quick. Okay, so when I select my logo here in the blueprint, I can see that the slot is a canvas panel slot, and it contains all the information regarding the position of the widget in terms of the canvas panel. And that's what we're going to use in order to position the widget on the position of the mouse. Let me show you guys real quick what I mean by that. Let's go into AdjustPosition, and we can see here that when I set the position, I'm not actually setting the position of the logo. I'm not doing something like this. Set position, there's nothing like that. I'm taking the logo slot. It's true that what I could have done here is I could have written cast to UCanvas panel slot logo slot, and then I can set position and then send the new position in widget scale. All right, I could have done that when I set the widget position on the mouse, but I chose to not cast every time and just store the logo slot as a variable. Next, one final thing that I do on the initialization of the widget is start widget position, the position at which the widget starts, the middle of the screen. I'm going to store it in the variable start position widget, which again, this naming convention means that this is in widget scale. Start position widget, okay, not screen. All right, getting closer and closer to the part where we start the physics simulation. Native tick. What happens on native tick? On tick, we're gonna check if the mouse is pressed. We're gonna adjust the logo, either its shear, its scale, or its position. Again, the way it works, when we play, I click somewhere on the screen and I adjust the widget whenever the mouse is pressed. When I let go of the mouse, it's going to start the physics simulation. So, on tick, if the mouse is pressed, we're going to adjust and return. We're not going to go to Spring. Spring is basically the function that starts the physics simulation. Maybe not start, but just physics simulation, because it's not necessarily going to start it, but going to continue it also until I press the widget, the mouse again, or until I reach the threshold, right? Okay, so let's start from adjusting. And we're going to start also from the shear because it's the most simple one. Okay, adjust logo, like we saw before, we get the mouse position in screen scale, we convert it onto widget scale, we get the mouse position widget. Then we calculate the amount to adjust. Now, I'm interested only in the change on the displacement on the X value. I don't really care about the Y value here. So, if the checkbox, SpringShear is checked. Okay, so if the checkbox here, SpringShear is checked, I'm going to change the shear, right? If the scale is checked, I'm going to change the scale. If the position is checked, I'm adjusting the position. Okay, so let's see how we adjust the shear. First, let's say that the shear is checked and we want to adjust it. I'm saying the new X value of the shear is going to be the amount that I adjusted with, right? The amount of the distance that my mouse is from the center of the widget, and I'm multiplying it by mouse effect, which is this arbitrary value that we talked about. Can play around with it. Currently it's 0.1 and it looks pretty good. Then I set the shear to be this. Why is there a minus here? Just because the shear value, when it's positive, it actually stretches the widget to the left, but I want the widget to stretch to where the mouse is, and that's why I put a minus here. This is the way Unreal Engine handles the stretch value. Now, after we've adjusted the shear and we let go of the mouse, let's see what happens when we call SpringShear, right? So if B mouse pressed, we adjusted the logo, we release the mouse, we're gonna call Spring. Now the Spring is gonna do something similar. It's gonna check which one of the checkboxes is true and run its behavior. So if the shear is true, we're going to SpringShear. And this is where things get interesting. And SpringShear is practically the physics simulation running on the shear values. First thing first, I store delta time, the time that passed between the previous and the current frame. I get the current frame's shear value, right? The shear that the mouse that I set while holding the mouse. The shear rest value is 0, okay? Meaning that the shear, when it's 0, this is the rest value. This is where I want the spring to relax, when the shear is 0. The shear displacement is the current shear position, meaning the current shear value that the mouse has been set or has been set by the physics simulation, minus the rest value. These are defined by Hooke's law. Then I check whether I've reached the threshold, okay? I'm gonna talk maybe about the threshold later because it also uses the velocity. Anyway, check if the threshold has been met, meaning whether there's any changes currently happening. Like I said, when the spring gets really close to its rest position, at some point I just stop doing the physics simulation. So here we're going to calculate the forces working by the spring in order to calculate the velocity, the change in position. So here, just for the example, I'm setting mass equals 1. The mass is always going to be 1. Just for this first calculation, I'm going to show it. The mass equals 1. We're calculating the spring force, which is from Hooke's law. It's minus the spring constant times the shear displacement. Here, because remember, we're calculating the shear. Generally, it can be the position displacement, the scale displacement, whatever displacement you chose. The damping force is the damping coefficient times minus the velocity. Okay, this is important because the velocity is supposedly a vector. Here we're using a one-dimensional velocity, but we always want the damping force to go against the velocity. So the net forces on the spring are the spring force plus the damping force or friction force, because this is actually how a friction force looks like. The spring's acceleration is going to be the net forces working on the spring divided by the mass. Okay, the mass is equals to 1, so we might as well have just written spring acceleration equals net forces. And then we take the acceleration over the time that passed from the previous frame. By using delta time, we multiply it and we add it up to the spring velocity. Now, this reminder here says to collapse into net forces, and since this is a function that we're going to be using for both the scale and the position, I'm just going to collapse all of this thing just into the function net force, and I'm gonna send in the shear displacement. Okay, and I'm going to calculate the spring acceleration like so, and I'm going to show you guys what this function net force does. It does exactly the things we discussed. Takes the spring force multiplied by the displacement, puts a minus in it just like Hooke's law, calculate the damping force, and returns the spring force plus the damping force, so the net force on the spring. We've collapsed the function, perfect. Now we're going to add the change in position, which is the velocity over delta time, seconds. So the new shear position is going to be the current shear position plus the change in position. The change in position is also frame independent. We're multiplying it by delta time, and this also acts as a sort of integration because we are adding up the values of the velocity over time, over delta time, a small amount of time between each frame. Then we set the new render shear to be exactly this new position, which is the current position plus the small change that we got on this frame. And again, we care only about the X value, the Y value I leave at 0. Alright guys, so let's back up a bit, this time to adjusting the scale. So when we adjust the scale, it's actually a little bit more interesting than adjusting the shear, and we're using this technique here, which I learned from Dream Job game dev tutorial, where the X value of the scale increases. As the X value of the scale increases, the Y value of the scale decreases. This creates this sort of squishy behavior. This time, the rest position of the spring for the scale is going to be 1 instead of 0. Okay, so because the scale starts from 1 and we want it to go back to 1, not to 0. So we take 1 scale, the scale of 1, and we add to it the amount we want to change it by when we adjust it. And actually the scale of Y is gonna be 2 minus scale of X. Meaning that once the scale of X reaches the value of 1 again, when it reaches its original state, the scale of Y is also going to be 1. But the more we increase the scale of X, for example, if the scale of X is 1.5, if X is 1.5, then Y would be 0.5. Okay, so we're actually having this negative behavior, this proportional negativity between them, creating a very nice effect. Now there's a small thing that I add here, which is the constraint on the scale not to flip, because I don't want my scale to flip when I adjust it. And I'm gonna also do the same here and uncomment this, and I'll show you guys what I mean. So if you guys remember, when I was scaling before I put the constraint on the size, I could flip the orientation of the scale. Now I cannot flip it, and no matter how much I scale the X value, it's never going to flip. It's never going to go on the other side. Even if I set the mouse effect to 2, it stays at this 10% of its size at most. And then when I release it, looks great. Okay. So practically, how does the constraint work? I set the scale of X to be the maximal value between scale of X and 0.1, meaning I'm never going to let it go under 10% of the size. Same thing I do with the Y scale. I don't want it to start flipping. Let's go to Spring Scale. Awesome. Now, when we spring the scale, we're gonna go through the same steps as springing the shear. We're gonna get delta time, get the current scale position this time. Of course, again, I'm calculating this based on the X value. The scale rest value, which like I mentioned, is actually 1 this time. It's not 0. The scale displacement is gonna be the current scale position where I left the mouse, minus the scale rest value, which is 1. I'm gonna check the threshold. Now maybe we can talk about exactly what checking the threshold means. Since we understood that the spring is gaining velocity and the displacement is changing, so when the displacement is smaller than the spring threshold, which is 0.001, and the spring velocity is smaller than the threshold of 0.001, Then I've reached my threshold and I stop the physics simulation. So on tick, there's not going to be any calculations being made for the physics simulation. Important things to note is that I do need both the displacement and the velocity to be 0, because when the widget is springing, we can reach situations, for example, where the displacement is actually 0. For example, when I let go of the shear, at some point the widget reaches 0 shear, and then it continues to the other side. And at this situation, just the displacement is not enough, because what happens is the displacement becomes 0, but the velocity is not 0, and it gives it more displacement on the next frame to the side. That's why I need both of them to be near 0. Awesome. To continue, let's continue. Yeah, so we check the threshold. We find out that we're okay. We continue the springing. We calculate the spring acceleration from the function NetForces, just as we did the same with the shear values. We integrate it into spring velocity. Again, here I don't divide by mass because the mass is 1. And we make a similar calculation to what we did when we adjusted. The new scale of x is going to be the current position plus the change in position over time. And the scale of y is going to scale accordingly. It's going to take 2 minus the new scale of x. Then I'm going to constrain them to not be smaller than 10%. And we set the new render scale. Awesome. And last but not least, we're going to adjust the position. Now, I put it at the lowest because I think it's the more... you can say it's not more complicated per se, but it uses vectors instead of values. And so I put it just down to get to it last, but it's actually better to place it here because we don't actually need this amount to adjust this calculation. We don't need it for the placement because we're not actually adjusting it according to an amount. We're putting the widget exactly where the mouse is. So when we're adjusting the position, I think we've been through this function. We just set the logo slot, pay attention, not the logo slot position, to be the new mouse position after it has been converted to widget scale. So spring position, delta time is the value of delta time, but this time, instead of using the current position as a shear value or scale value, we're actually going to get the current logo slot position in the canvas. And it's going to be a vector 2D. The position displacement this time, instead of being a value like shear displacement or scale displacement, is going to be a vector. It's going to be the position of the widget compared to the position in the center of the start position. Pay attention that when I get the position from the logo slot, it's already in widget scale. That's why here the position displacement is calculated using the current position, which is in widget scale, minus the start position, which is also in widget scale, okay? Maybe I can add this also here, just to make sure that the naming convention is kept. So we've got current position and widget, so it's widget scale. Okay. Now let's get to an interesting topic, maybe in C++. If you listen up to this point, reach threshold is actually gonna get this time, instead of getting a displacement that was a float, it's gonna get a vector. When you've got a function with the same name but a different signature, a different parameter that it's getting, it's called function overloading in C++. So for those who want to skip this part, I'm going to explain what function overloading is and what it looks like. I've got two functions here called ReachedThreshold. Both of them return bool. They both have the same name, except the first one receives displacement as a float, and the second one receives a displacement vector. Then what the second one, the overloaded one, does is it calculates a displacement size based on the size of the vector, a velocity size, which is actually based on the Spring Velocity vector variable instead of the Spring Velocity float variable. And it makes the same comparison to make sure that we're within the threshold to continue the Spring simulation. And this is how it's declared also in the H file. We declare it the same, and we make sure that the signature or the parameter list for the function is different. Cool. The same is actually going to happen on the next line, because what I do here is I calculate the spring acceleration, which is going to be a vector this time from the function NetForce. But we remember that the function NetForce was also receiving a value of displacement. This time we've got an overloaded function NetForce, which just does exactly the same as the NetForce that receives a float, except this time it's gonna use F vector for spring force. Remember that force is also a vector. It has a displacement vector, the displacement from the position of the center of the screen minus the spring constant. We multiply this as a Hooke's law. The damping force is gonna be gonna have the exact opposite. This is why we've got a minus here. The exact opposite direction of the spring velocity multiplied by the damping coefficient, and we return this vector, which spring force plus dampening force is a vector this time. So this overload actually has both a different signature, but it also returns a different value. This one returns an F vector 2D. So when we calculate the net force here, we're getting a vector, an acceleration vector. We multiply the acceleration vector, we scale it by delta time. We calculate the spring velocity from this, and then we know that the new position is going to be the current position plus the change of position over delta time, which is the velocity multiplied by delta time. And we set this as the position for the logo. I hope this is clear enough. Practically, this is all there is to know about the C++ side. There's a tick function that either adjusts the widget or plays the physics simulation. Now let's go over the blueprint side of things and see how the class that is inherited from this C++ class that we went over acts in the blueprint. Alright guys, now let's go over this class, which is the blueprint that inherits the C++ user widget class that we just went through. Let's go into the graph and talk about what we see here. So on preconstruct is the event where I overwrite the variables that I set here, that I wrote OnInititalized. I wrote that they can be overridden in the editor, meaning that what I do here on construct, I take the text from the editable text constant from the damping coefficient, and I convert it to a float, and I put it inside the variable that is actually inherited from the C++. If you guys go to the side panel here, we can choose to show inherited variables or not to show them, and the variables under the category Springs tutorial, we can see our category, our variables from C++, spring constant, damping coefficient, and mouse effect, which I'm setting here. Now, this get value as float function does exactly this. It's just a function that I wrote to shorten this logic. Yes, I like my blueprints to be sort of organized at least. Perfect. So first thing we do on preconstruct, and by the way, the preconstruct event, like I said, it runs after the onInitialized event. So the onInitialized event is actually the constructor that we're used to from other objects. OnInitialized, I set up the checkboxes array. I just have a variable called checkboxes array to which I add all of my checkboxes from the widget. Why do I do this? I create an array of checkboxes because later on, when I check one of the boxes, I want I want the other checkboxes to be unchecked. So I'm gonna loop through the array. Whenever a checkbox is checked, I'm gonna loop through the array and uncheck the other checkboxes, just like so. All right, so this is why I set up the box array from blueprint on initialized. Now let's get to the interesting part. Whenever I change the text, like I said, in real time, I convert it to a float and I set the variable for the physics simulation. So when the editable text is changed, I'm setting the variable. Next, whenever a checkbox is checked, I check if it's true. If I checked a checkbox to be true, I'm gonna uncheck the others. Then I'm gonna also set the variables. These are the variables from C++. I'm gonna check them to false for the simulation. And also when I check a box, I reset the logo, which is the C++ function, which I set as, I think it's the only function that I set as uFunction blueprint callable, which means that this is accessible from the blueprint. Only this function from all of those functions is accessible from the blueprint, exactly for this need, so that whenever the simulation is running, okay, if I check a box, it's gonna stop. Again, whenever the simulation is running, I check a box and it stops, and I start again. And whenever I press the mouse, again, I stop the simulation, I stop the velocity, and this is how it goes. Let's put here 3. Perfect. All right then, that's it for the widget side. I hope it was clear. You guys let me know. And thank you very much for watching. Again, the U project Git repository is in the description. Feel free to use it for whatever you want to use. I would appreciate it, of course, if you can share some attributions if you were gonna use it. And that's it. Feel free to ask any questions. Alright guys, so before I let you continue to your wonderful days, I want to show you how I implemented the same physics simulation here in my game submission for Ludum Dare 57 Game Jam. So as you guys can see, I've got this red blob here on the screen that follows the white circle, which is the position of my mouse. It turns towards it, and whenever I press my mouse, we can see that the blob is filling up, like inhaling or trying to swim. Maybe that's what I was trying to represent here. And it starts to stretch forward when it starts swimming. And whenever I release my mouse, it actually creates this Spring physics simulation that we just went through in the widget. Now, other than that, springiness that's supposed to resemble the blob swimming in the water, the yellow spheres that follow actually use a technique of procedural animations to follow up like a snake behind the red blob. So this is maybe a topic for another time. Again, thank you guys for watching. Feel free to leave comments, questions, download the repository, try this Zooid Nexus game, which is actually, I hope, quite fun, and it actually is based on something called siphonophores, which the game contains a little bit of information about them. They are real creatures, which I try to represent. I think I completely failed at it, but I hope that my intentions were good. That's it, so keep calm and develop.